In the last class, we looked at the type of equalizer that we need in order to equalize a low pass channel, right? Because of low pass characteristics of the channel, the continuous time impulse response looks like this, and the discrete time impulse response generally looks something of this sort. It has a cursor whose amplitude is reduced because of the low pass effect, and also it has these intersymbol interference tabs. Okay, and especially the one before and one after the cursor will be positive. After that, it's hard to say. It's a purely low pass filter like thing. They will also be positive, but they can be negative. Okay. And to equalize this, let me, for simplicity, make this 0, the precursor tab 0. To equalize the channel like this, you will need an equalizer which has a response of this sort. That is, a cursor followed by a negative tab. Okay. This gives you a high pass magnitude response. In the frequency domain, this looks something like this, and this one has the opposite shape. Okay. This is the channel, and this is the equalizer, and you can have more taps on this. Okay. And the convolution of the two should look something like this, but we also know that we can't get it completely this way, so there will be something of this sort. Similarly, in the frequency domain, it won't be absolutely flat. It can do something like this or something like this, but it will be flatter than what the channel was originally. So this is in the frequency domain, and this is in the time domain. We also came up with an algorithm for choosing the taps. We firstly said that the number of taps in the equalizer must be more than the number of significant ISI taps in the channel response. Okay. I say number of significant taps because you can have a truly infinitely lasting response, so you won't have infinite number of taps, but we will look at where the response becomes negligible and truncate the response to that many taps. And the larger the number of equalizer taps beyond this, you can reduce the magnitude of the ISI further and further. Okay. With the number of equalizer taps equal to the number of taps in the channel response, you can make a response which has a single one, a lot of zeros, and at the end you have some residual ISI. And that residual ISI is what you can reduce with increasing the number of taps. Okay. If you increase the number of taps, you will have more taps in the combined channel plus equalizer response. There you set all the intermediate values to 0 to find out the tap weights. After that, the last one that remains will have a smaller weight. Okay. You set the channel plus equalizer taps to 0, and you can't do this for everyone, as many as possible. Okay. So let's just go through the steps quickly again. If you look at the response to a single pulse, the response of the channel looks something like this. If you send in a pulse of unit amplitude, you will get a cursor which is less than unity. Okay. This is because of spreading of the energy over other taps, and you will get something like this. And just for illustration, I will again take a response that has only 2 taps. That is, I will only consider this and this. The simplification is only to enable me to compute the algebra easily on the board. So the channel impulse response is H1, and H0 is less than 1, and H1 is greater than 0. And let's say we convolve this with a 3-tap equalizer. Responses are G0. What are the resulting taps? What is the first one? H0, G0. The next one? Plus H0, G2. The next one is G1. Yeah. And the next one is H1, G1 plus H0, G2. And the next one is H1, G2. In this case, we reduce these two to 0 and we want to make the main tap 1. Okay. G of 0 is 1 by H of 0. So what will be the magnitude of G of 0? Greater than 1. So that is one thing. Also, you need some kind of a gain in the equalizing filter because the cursor amplitude has been reduced. If it's followed by a decision block of the same sensitivity as before, let's say you have a transmitter and you have no channel or an ideal channel and you go to a slicer. The slicer has a certain sensitivity which will determine the bit error rate. Now you have a channel between the transmitter and the receiver. The amplitude of the cursor is reduced. So you need to increase the cursor to the same amplitude before you apply it to the slicer because the slicer has a fixed sensitivity. Okay. In order not to reduce the BER, it's not enough to have a single cursor and all the others 0. The amplitude of that should be sufficiently high. Okay. That's what we are trying to do here. We will assume that there should be 1 and these two should be 0. And what is G of 1? Minus H1. And what is G2? So if H0 is much smaller than 1, then each of these taps also has to be larger than 1. And I mean, say it becomes larger and larger as the value of H0 keeps on reducing. So the equalizer response can be written as 1 by H of 0, H1 by H0 Z inverse plus H1 square by H0 square Z inverse square. Okay. This is to make all the intermediate taps in the equalized response 0. So you can see that the weights of Z inverse and Z inverse square depend only on the ratio of H1 to H0. So that makes sense in a way because if you increase all the taps or reduce all the taps, the amount of ISI in a relative sense has not increased. Okay. If I have a response like this, let's say this is 0.5 and this is 0.1, or if I have, this is 1 and this is 0.2, you can intuitively feel that these are equally bad channels in that the amount of intersymbol interference is the same. Okay. That depends only on the ratio of this to this, isn't it? Because this is the one that's contributing to the desired symbol, that's the contribution from the desired symbol, and rest of these are the contributions from the intersymbol interference. So if the ratio of these two is a constant, the amount of intersymbol interference is a constant. And to that you need to have a gain of 1 over H of 0 so that you can restore the amplitude of the cursor to the same level as before. This is to overcome the sensitivity of the slicer. Why did you measure it in power? No, why do you do that? Yeah, but now what is the significance of the square as opposed to the quantity without the square? No, I know, but why do you say that is the measure of ISI and not this one? Yeah. No, SNR is different. So you shouldn't confuse the signal to noise ratio with this, right? The signal to noise ratio that appears in the bit error formulas, basically Q of SNR is the bit error ratio. That is the ratio of signal to the random noise, not this ISI. The signal to ISI will not give you this one. Okay. This is the signal to ratio of that noise which is Gaussian distributed with an infinitely long tail. That's what gives you this formula. No, it won't, it's not very precise to say that. What ISI does is, let's say, it will correspond to this value. Because of ISI, it can be something like this. So what it will do is, increase what it will change in fact is, so this is noise, which has a certain variance, it will reduce the amount of S. Okay. That's what it does. No, that is perfectly fine. That is correct. So you can say that reduction in the signal voltage is the same as the increase in noise also, right? So all I'm saying is you don't necessarily have to take the ratio. You don't necessarily have to take the square of the quantity. Okay. If H1 by H0 increases, H1 by H0 square also increases. You can use either measure. But what I was trying to say was the ratio of H0 to sum of all these square, that is not the SNR. Okay. The SNR is the ratio of this, the received amplitude to the sigma of the noise that is added. That is the SNR that you have to plug into this formula. Okay.
But if you say we have a sequence of data,
yeah,
and that also in a real time system, like the data is keep on incoming and increasing.
Yeah.
At the same time, data is taken out of the channel also.
Yeah.
So how do we do for that convolution now?
Yeah, I mean, what we have the response to a single pulse. How do you find the response to a bit stream?
That is like it depends. Like we have the sequence of bit stream. How many? Well, after how much time instant are we seeing this? That many bits will be there on the channel.
Okay.
And then convolution to the H will give me the output at that instant of time.
Okay. So, are you saying that it is not the same as adding the pulses? I apply this is a channel. I apply a single pulse and I get something out. For the bit stream, I have something like this. Okay. Which I think of as one pulse plus or minus this pulse plus this and so on. So I can take this and overlap and add. Will that not give me the response?
That will give me the response, but I have taken into account that we like if the bits are transferred, like I am also taking the bits out from the channel.
Yeah, sure.
So that extraction rate and number of bits that current instant on the channel.
No, that is included in the response, right? As long as it's a linear time invariant system, this is always right. Isn't it? So maybe if the channel has a delay, okay, which is I think what you are thinking about. You have a transmission line which has some delay. So then the response to a single pulse may be something like this. It has a delay. Then if I want the response to a 1 minus 1 sequence, I'll take this, shift it by 1 bit interval, flip it and add it, isn't it? And then let's say I have 2 more ones, then I take 2 more of these and add the whole thing together. So it's not that you are putting something into the channel and you are squeezing it out or something. Okay. The response to every bit is in the channel, probably for infinitely long time. But as long as you are convinced that it is linear and time invariant, they should be okay. Is it or is it not okay?
I feel like after like if suppose 10 bits we transfer at each every second.
Yeah.
And the delay or there is some delay in the channel.
Yeah.
So once like this 10 seconds have passed,
Yeah.
10 bits have passed, they have no effect on the incoming bits. Means if the data is already extracted out from the channel.
No, but what is extracting out? This is not like squeezing toothpaste out of the tube, right? It's not like there is some material stuff in there. And actually there is something in there, in that, what does this response mean? If you have, in fact it may be more like squeezing toothpaste out very slowly, at the end it's very hard, right? So, the fact that the response to a single pulse is like this, after, let's say you said 10 bits, okay, there is still some residue remaining, okay. If I transmit a bit now, firstly there is this delay TD, and then let's say this is 10 times TS, okay. After TD plus 10 TS, I can still see the effect of this bit. There is nothing wrong with that, right? So it's not like by taking the bits out, you don't really take anything out, you simply look at the value of the voltage. It's not like you are resetting the transmission line, you are shorting it out and reducing all the fields inside the transmission line to 0 at that point. You send bits one after another. So this bit will have an effect. At this point, you will start seeing an effect only after TD. That is because of the finite speed of the wave. And it has some effect after 10 TS also. That depends on the actual characteristics. But let's say the response is infinitely long. So it will always have some effect, even at infinitely long time. Okay, maybe it is small enough, but it will always have an effect. It's not as though after you transmit this, let's say you receive this and then you reset the transmission line. You just keep on sending the bits. What it does is basically let's say this is 0. So at 10 TS you send another bit. The initial condition for this, analyzing this bit, depends on this one and the next one and the next one and everything. Okay. So we are not resetting the transmission line. Is that okay? And the reason you can have precursor ISI is, a lot of precursor ISI also is because, let's say the response to a single pulse looks where this is the bit interval, and the response to the next pulse would look something of this sort. So in a way, the peak of this pulse is here, the peak of the next pulse, this pulse is here, and the second pulse has significant contribution even at the peak of the first pulse. So you can have effect on symbols before and after. That's because you can have a lot of delay. At least there are filters which have pulse responses like this. Okay. There are two filters which have the same magnitude response, but one of them can have a pulse response like this, the other one can have it like this. Do you know what they are called? Okay, think about it. It's possible. You can have filters with the same magnitude response and different time domain responses. And there is, yeah, it will have a different phase. What about it? Okay, any questions on the equalization and how we chose the taps, etc.? Is that the best? Did you try out something else? I mean, we had a certain way of choosing the taps. That was to make the intermediate ones 0. Okay, whatever we can make 0, we make 0. Is that the best that we can do? Okay, will it give you better stuff? So let's see, you are saying that we will minimize the powers in those other taps. So the responses were H of 0 G of 0, H of 1 G of 0 plus, sorry, H0 G1 plus H1 G0. In fact, let me simplify this whole thing by taking only a 2-tap response and a 2-tap equalizer. So the channel response is H0 plus H1 G inverse, and I want to multiply this with G0 plus G1 G inverse, and the result I get is H0 G0 plus H1 G0 plus H0 G1 plus H1 G1. Okay, we get a 3-tap response, and we make the cursor to be 1. So the value of G0 is fixed to 1 over H0. So I get 1 plus H1 by H0 plus, sorry, H1 times H0. No, it is H1 by H0. H1 times H1 by H0 plus H0 times G1 Z inverse plus H1 G1 Z inverse square. The question is how to choose G1. That's all. That's all that we have to do in this case. Before we made this whole thing equal to 0, the Z inverse coefficient. Now we will do something else. We will try to make the square of this plus this to be the minimum value. So I will minimize the mean square of this. I will define to be the error, and I will minimize this error. Okay. What do I minimize this with respect to? G1. And what is the derivative of this with respect to G1? 2H0, 2 times this times H0. And this one, and I make this equal to 0. So what do I get for G1? Minus H1 by H0 square. What's the numerator? H1. No, there is something wrong with this. This is minus H1 times H0. H1. So it is correct actually. H1 by H0 square plus H1 square. Is this a minimum or a maximum? How do we know? Yeah, it is a minimum, it turns out. Yeah, actually we will come to that. It is true. It's not like adding the square. So this will give us this. And what will be the response of the total equalizer plus channel? What will be this term? I think we'll simplify the algebra by making H0 equal to 1. Okay, it doesn't change anything, right? So we'll get H1 minus, this is H0 is 1 and G1, which is H1 by 1 plus H1 square Z inverse plus H1 times minus H1 square by 1 plus H1 square. So let's take an example. H0 is 1 and H1 is 0.5. So in the first case where we reduce the intermediate tap to 0, what would be the tap weights? So first one, reduce intermediate tap to 0. This is the method that we discussed in the previous class. What are the equalizer weights? What is G0? 1. What is G1? Minus 0.5. Okay. And the convolution of the two is this correct? Or minus? This should be minus. Okay. Second one is to reduce the sum of squares. What do we get? 1 plus. So this will be H1 cube by. So the first one will be H1 0.01 and the next one minus 0.2, 1 by 7. No. 1 by 5. So this is what. So which is better? First case is better. Why? Yeah, if you just look at the worst case, the first one seems to be better. But you can't make a general statement like this. So if you have this, you will have 3 values for the, or you will have 2 values, right? For the, let's say you want to receive a logic level of 1. What are the values that you can get? So depending on whether the 1, 2 symbols before was either the same sign or the opposite sign, you will get either plus or minus. So you will get either 1.25 or 0.75, and in this case it has 4 possible values. What is the worst? 0.7, or you can get 0.9 and 1.1 and 1.3. Okay. So the worst case is worse here. So minimizing the sum of squares of the equalized response taps didn't work. What should we have minimized? No, actually this, see, in the first case we reduce the intermediate taps in the combined response to 0. So that made sure that the response from every, like the previous tap and the one previous and so on, were all 0, except for one particular one at the end, right? In this case also we went and minimized the mean square value of the equalized response, but that's not what we want. What we should do is see the possible values that we get for the symbol and minimize the mean square value of that, isn't it? Actually what he said was right. If you want to minimize this, I mean if you want the largest amplitude for this, for the worst case, then you should minimize the absolute sum of the taps in the response. Okay. So I shouldn't say to minimize, I will say to maximize the worst case received voltage. I should minimize. This is channel plus equalized response. So basically n excluding the cursor. Okay. Because if I transmit 1, the worst case that I get is 1 minus this summation of the absolute values. Okay. That is the worst case. But that is also not what I want, because I get a whole spread of values. So I want to minimize the composite effect of everything. Okay. So I can try and minimize the mean square value of the distribution around this as well. Okay. Which will give you something equivalent, because we have 1 and for every value that is below this there is something above it. Is that convincing? Because if all the intersymbol interfering bits are of the opposite polarity, you will get something above that. So to minimize the spread around this one, I can also minimize the mean square value of these points. Okay. The algebra is complicated, we will do it later, but that is the type of equalizer, that is another possibility. Okay. You minimize the mean square value of the possible responses to 1. No, I maximize the worst case received voltage, that is, if this is the worst case, I want to make it as large as possible. In the other case, what I said is I want to minimize the mean square value of this distribution. That is, I would like this distribution to be rather skinny. That means the values are closely around 1 rather than something like this. Okay. And we have not worked through the math formally, but that turns out to be more optimal. Okay. So we will discuss this like more in detail, like how this whole thing comes about and what effect it has on other aspects. So one of the things we have not considered so far is how these things behave in presence of noise. Okay. So if you try to force the taps to, let's say, 0 during the first using the first method or using the second one where you minimize the mean square value, it has a different effect on noise. In presence of noise, it has a different effect. So that's why one is preferable to the other. But we will see all of that in detail. This at least gives you some kind of heuristically some methods for computing the equalizer taps, and you can use that in the assignment to figure out what the taps are. Any questions on this? Yeah, that's correct. Yeah. So if you know the channel response, you can calculate it beforehand and preset the equalizer taps. If you don't know the channel response but know the possible ranges, let's say, at least that you should know, right? It will not be completely arbitrary. Yeah, that's correct. So we'll need to automatically set the values. Okay. So one way of setting the values is, for instance, let's say at the sampling instant you receive a set of voltages. Okay. And you measure this voltage somehow. Let's say you have an A to D converter which measures the received voltages. You don't just say it is +1 or -1, but you actually measure each of the received voltages. So you can build this distribution as well. And you can go on by brute force by changing the taps, try and minimize the RMS value of the distribution. So that is one way of making an adaptive equalizer. Of course, we won't use a high resolution A to D and then we don't by brute force try all the coefficient values to minimize it. There are algorithms to drive the taps in that particular direction. That is known as adaptation. And there is also the other algorithm where you try to make this exactly equal to 1. Okay. So that what happens is in reality you get a continuous time waveform and the eye diagram looks something like this. So it can have many possible transitions, 0 to 1 and 1 to 0 and so on. And if this is the sampling instant, you get a bunch of values. Now you are only now considering what you are going to do to these values, whether you will minimize the mean square value of that or whether you will make that equal to 1. So that has an effect on what happens in the other parts of the response. Okay, how sensitive it becomes to noise and etc. So that's where the difference between the two algorithms comes in. But there are algorithms which can drive you to bunching all of them to a given value or to minimize the mean square value of that. So in a way it doesn't matter, right? So you have a delay for the cursor. Let's say you have an eye. Let's say this is your eye diagram. Okay. So this will be the sampling instant. Now it doesn't matter if this came from the first tap or any tap, any delayed tap. What I mean is, so let's say the response looks something of this sort. Okay. So where you find the peak value is the cursor, that's all. So was that the question, like how do you find the cursor? Or? Yeah, so if you look at the eye diagram and let's say these are the sampling instants, you define this where it is open to be the sampling instant. How we'll do it, we'll see later. Okay. Once we do this, we don't really care if a particular sampling instant is for the nth bit or the n plus 1th bit. isn't it? So that only increases the delay of the whole thing by 1 bit. That's all. So if the response was, let's say, like this, then the delay of the entire chain would be this much. Now if it is this way, it is 2 bits more. We are supposed to receive only the sequence of bits in the same sequence correctly. How much delay is there between the two? For now we ignore. So that's all that does. If there's a lot of delay, there will also be delay in the received signal. Anything else? No, minimizing the sum of squares of what? The equalized response. No, minimizing the sum of squares is actually minimizing the partness of the distribution in some way, right? So let's say this is 1. You measure the errors from 1. Okay? So it will be both positive and negative. You take the sum of squares and minimize that. What will happen? That actually minimizes the spread. Isn't it? Any other questions? Okay, we'll make this more formal and clean as we go along. But heuristically, you should understand how equalization works. You have post-cursor ISI. So you try to subtract off this one. So that's why you need the negative post-cursor tap in the equalizer. Okay? That's the idea. How much exactly you make the tap, that depends on different measures of error. Okay? The first thing may be, I'll reduce this completely, I'll make it 0. Then you see that you have some residual term left out afterwards. Okay, so maybe you try to minimize the composite effect of the 2 taps. That's what you try to do by minimizing the sum of squares around this 1. Okay, we'll meet in the next class.